The moon is falling. Got some stuff for you. There were some proteins, amino acids that we missed last time, so we're going to add L-ornithine, carnitine, seleno, that's going to be selenium with a cysteine, instead of the sulfur, and citrulline. So these are the boring ways that they draw it. We're going to do it the fun way with the Schroeder triangles. So let's start with reviewing. Do you remember any of that stuff? Carbonic acid, that's the CO2 that's in the water all around the world. So it's the CO2 concentration in the atmosphere goes up. What do you think happens to the acidity of the water in the oceans and everything? More CO2 is pumped in, more carbonic acid is made, so it becomes more acidic. This is water. Remember, it looks like Mickey Mouse. There's our Schroeder diamond. That's a one carbon with 3 oxygens around it. 2 of these are charged, so there were 2 protons, which means it's diprotic. So let's review here. We went through, we did our amino acids, drew them. This is a one-man show here, so we're rolling everything. If you could see behind the scenes here, we got 30 cables. We're tripped up around it, and we're holding the mic because we knew we would just walk away and end up pulling it out. So this was our amino acids using the Schroeder Diamonds to make it all easy. So I hope this looks familiar to you guys. See how much easier it is here? Here's alanine, one of the simplest ones. All it has is a methyl on the end of the peptide backbone. Glycine, all that has is a simple proton dot. So that's probably the simplest amino acid there is. So remember when we came along and did these. Now leucine, we're going to count the carbons on the end of that. 2 methyls are the carbons on the end hanging off. So you got a methyl, methyl, 4 carbons overall. Now where's our regular leucine? Okay, leucine somehow. Boy, it must be nice to have a crew here that could hold the cables for me as I roll along. Anyway, here's leucine with 4 carbons again, but see, they're in a different configuration. There's 2 methyls on the carbon in the middle. Over here, isoleucine has the methyl right on there on the beginning. The first carbon has a methyl on it. And then compare this over here. So these are called isomers because they're still the same number of hydrogens, same number of carbons, but they're just arranged different. And remember, these are 2-dimensional drawings because really, ideally, what we were dealing with is a 3-dimensional thing. We'll show this a little bit better. Oh, this is so dumb. The lens cap hangs and then it gets stuck. I pulled it up 3 times. We'll show this with some better lighting later. We're trying to conserve electricity here. Plus it gets hot as a dickens. How hot was it? So, we're coming across. Here's our simple amino acids, the way we drew them. And we keep this hokey. This is all on recycled paper, recycled pens, all this. So someday we'll do it up really good. But right now we're just showing you the basics. Whenever you see yellow, it's going to be sulfur. So you see here methionine, carbon-carbon, sulfur with a methyl on the end there. Okay, there's 2 amino acids that have sulfurs in them. And look at this one. That's just got 1 carbon with a sulfur on the end. That's the equivalent of an alcohol. Because remember, sulfur is in the same group as oxygen. And it's just got a proton on the end of it there. It does the octet bonding, all that. So there's cysteine. The other sulfur-containing amino acid is methionine. So quite a different character there. The only 2 was sulfur. There's 2 carbons, sulfur with a methyl on the end. This is just a carbon with the sulfur on the end. A sulfuric alcohol. That's not a proper name for it. Now the alcohols, if you recall, was just having an oxygen with a proton on the end. So what we did was we're making this to be a red dot with a green circle around it. There's a methyl hanging off it. So this is what you'd call an internal alcohol. So usually alcohols are hanging off the end, right? So this is considered polar. So see, when we do our little charts here, we can write polar, we can write alcohol. You know, I mean, people don't even memorize these things, but it's good to become familiar with them. And I'll tell you, kids, I've learned a lot just from doing this. I just rolled the wheel over it. I just stuck my old... Okay, anyway. Polar, serine. Now, serine's got that terminal alcohol, as they call it, right on the end there. 1 carbon, terminal alcohol for serine. Threonine, if you recall, has an alcohol on the first carbon, but there's a methyl on the end of that. So compare here, cysteine is just like serine, except instead of an alcohol, there's a sulfur. Now tyrosine, see, we're not afraid of big rings anymore, are we? We can draw our carbon structures. We're not chicken. So there's a carbon, aromatic ring with the alcohol on the end of it. That, my friends, is tyrosine. There's another amino acid that has a ring with no alcohol on the end of it. And that one is phenylalanine. 1 carbon, the ring. So if you had an enzyme that's able to put a alcohol right on the end of that, it's got to be that carbon. It can't be any other ones on there. You could turn phenylalanine into tyrosine. Boy, this is really impossible. And then they got these headphones in the way. This doesn't help on the camera. If you could see what I'm lugging around, folks, you'd realize. Okay, so here is another polar side group. 2 carbons, a nitrogen with a double bonded O. Now see, what they don't draw in here is those lone pairs of electrons. So if the 2 lone pairs of oxygen are drawn on there, and the lone pair on that nitrogen, see, we didn't do it there, but that's the alien. If you remember the alien, nitrogen alien. We got them over here. Let's hold them in. See, if you remember really how nitrogen looks, it's got that lone pair of electrons up top. Can we get this one better? Because this has all the bonds on it. So this is what the nitrogen looks like. It's got a lone pair of electrons out there. Well, glutamine has that too. So what that means is the aqueous environment, the water, your blood, this will be able to float around in it. It's the hydrocarbons. If there's ever an example, see these hydrocarbons as they call them, say leucine for example, these are oil in water they call them, aliphatic. They do not dissolve, they do not like water, they call them hydrophobic, they're afraid of water. Some say water loving, water hating. I don't know if I want to go to that extreme. But doesn't like it. Oil and water. That's where you need an emulsifier. People that cook, what is it, mayonnaise and something else, you got to get to make vinegar, I guess, isn't one of them, isn't it? There's oil and another one that they get to make mayonnaise. I don't prefer like it, so I don't care. Anyway, we're back to the polar. This is an aldehyde. So this is what I wanted to show you. Even I make mistakes. We drew that aldehyde like it was an alcohol, right? There's no proton available to play in the game. So what we want to do is just color that in all together, see if that'll work. Okay, there we go. Okay, so an aldehyde on the end. See, like that.